Okay, great. So let me just double check and make sure that, okay, good. Well, I'm going to keep it on this mode rather than presentation mode because I have enough things to move around here without escaping out. So like I said, the units aren't that long, but they're really big. And so we're going to focus tonight on resistors in series and parallel, and then we'll tackle Kirchhoff's rules when I see you in person next week. And then these pieces actually go relatively quickly. But Kirchhoff's rules are definitely a place where people start re-examining why they decided to take physics. So we'll start off with EMF and terminal voltage. We talked about this last time. I just said because physically, it's almost like friction in the case of motion. There's always some kind of friction present. So resistance in a battery is almost always present. And it gets worse as the battery gets older. We talked about that before. So here's the heavy lift. We're talking about resistors in series and parallel. So if we have a combination of resistors like this, we are asked to evaluate the overall load. Now you can remember that back when we started doing circuits and everybody was doing such a killer job, the one thing that really wasn't resolved is that how do we find out the source resistance? Because it seemed really kind of complicated and not easily predicted. And that's what we're going to focus on tonight. And we're also obviously starting to draw these circuits in a more circular way. And in series, we know that the source voltage is the sum of the voltages across each one of these little loads. But the question is, what's the overall load like? In series, the current through each device is the same, obviously. And if we add up all those voltages, but then make a substitution for Ohm's law, we can see that the equivalent resistance in series is found by just adding the resistors. And that makes sense. This is consistent with our model for resistivity, where resistance is proportional to the length of our device. So by adding additional resistors, it's almost like we're just making them longer. For parallel, though, it's a little bit different. So in this case, we know the thing that adds up is current, that the current through each one of the resistors is going to add to equal the total current that's produced by the battery. So again, if we make the substitution for Ohm's law, but now we're substituting into current, so I equals V over R. And then, of course, all the V's are the same in parallel, so they all cancel out. And that means that the equivalent resistance is equal to the sum of the reciprocals. And that's a little tricky too, because we have to remember that after we do 1 over plus 1 over plus 1 over, then we still have to invert that final answer before we're done. But again, another way to think about this is our model for resistivity. And resistance says that resistance is inversely proportional to area. And so having lots of resistors side by side is kind of like increasing the area. So that kind of makes sense. That bears out. And so let's take a look at a couple of simple examples. So I'm going to stop sharing and I'm going to switch cameras so we can take a look at the whiteboard. Okay. Now the circuits I'm going to draw on the whiteboard tonight are just going to be freehand. And so if you're following along, I'll try and anticipate the fact that that you're trying to recreate this circuit as well. So I'm going to draw it pretty big. We'll start off with two circuits that have two resistors, and we'll do a combination in series and a combination in parallel, and we'll see how they're different. So we'll start off and let's do a 12-volt source. And we'll do 2 resistors like this. That's in series. And then over here, we're going to do 2 in parallel. Also 12 volt. And we'll do for resistances, let's do 8 and 12. Yeah, that'll work. So 8 ohms and 12 ohms. And what I'd like to do is I'd like to find out how much current is going to be flowing through the circuit. What is the current that will be provided by the source? Right, so let's do a little chart here, and I'm going to do, we'll sort of label our device. Let's go and then we'll do V, I, R, and P for each one. And so we'll chart here. And our chart's only going to have 3 rows because we just have our battery and we have the 2 resistors. And then we'll do the same thing over here. So we'll go device, and then V, I, R, and P. So we'll call this the source, and R1 and R2. Source and R1 and R2. Well, let's take a look at the numbers that we have to work with so far. So we know the source voltage is 12. And then we know the resistances are, I'm going to write 12 and 8. And we want to see what is the impact of being in series or in parallel. So 12 and 8. And this is 12. Okay, so if I could just see like a reaction, a thumbs up that you're able to see this okay? I don't want to go forward unless you can see all right. Okay, good. Thank you. So let's do our equivalent resistance calculation. So REQ in series is just the sum of the 2. So that's really straightforward, 8 plus 12, and so that equals 20 ohms. So the resistance that our source sees is 20. Now, of course, you'll remember that we have these relationships. We have Ohm's law, so V is I times R. And power, I'll get out of your way in a second, is V times I. So we have those. And that means that with any of these rows, once we know 2 things, we can figure out the other 2. Very easy. But before we start solving things on that board, let's take a look at the equivalent resistance here. This is going to take a couple of steps. So 1 over REQ is equal to 1 over 8 plus 1 over 12. And then we have to add those two fractions. So I don't want to bring up any, pre-existing trauma that there might be from finding the lowest common denominator from middle school, but it's the 21st century, so we can. This is, if we did do a lowest common denominator, it would probably be 24. So this is 3 over 24 plus 2 over 24. But like I said, 21st century, so we can actually just do our calculators like this. Inverse 8 plus 12 inverse. And let's see what that comes out to be. And so I get 0.208. Now it's important to remember that we still need to do one more step. We can add these reciprocals, but we still need to take the reciprocal of that in order to figure out what the answer is. So answer to the -1. And I get 4.8. And so the resistance is seen by the source is 4.8. Now that's going to tell us what the current is for each one of these. So the load, or effectively what the source sees, is a load of 4.8 ohms. And it delivers enough current in order to satisfy that. So I is going to be 12 divided by 4.8. And so that's 2.5 amps. We'll come over here and do the same thing. So 12 divided by 20. And that's only 0.6 amps. But that's okay, that makes sense because the effective resistance here is almost 4 times bigger than the effective resistance over here. And so we're going to have less current flow. We're also going to have less power drawn. So 12 times 0.6 tells me the power output for this circuit is 7.2 watts. And the power output over here is 30 watts. That's consuming a lot more power. Okay, how's the rest of this work? Well, we want to think about what is the same in series. What do we keep the same? And the answer is the current. So I have 0.6 going this way, but it's a single path. So the current through each one of these has to be 0.6. All right, now we can, of course, once you know two things, we can figure out the rest. So 0.6 times 12 is going to tell me the voltage drop for R1. That's 7.2 volts. And times 0.6, and that's 4.3 watts. We'll just do to the nearest decimal. And then 0.6 times 8, and that gives me 4.8. And 4.8 times 0.6 is going to tell me the power there. That's 2.9. And we're done over there. So that's great. Let's pause for a second and just do a couple of checks, because there are several things that we know here, and we can use those pieces of information to just double check our work. For example, conservation of energy says whatever power the source is pumping out is going to be dissipated in these two R's. So 4.3 plus 2.9 is 7.2. Check. So that's right. That's conservation of energy too. So no matter how complicated our circuits get, that's always going to be true. And then again, we know that the two V's here are supposed to add up to 12. So 4.8 plus 7.2 is indeed 12. Okay, so that checks out. Okay, now we come over here and want to think about for parallel, what's the same? And so we know that the voltage drop across each is the same. And each device is going to draw a current based on what its resistance is. That's how come your house is wired up in parallel. Because if it was wired up in series, well, first of all, everything has to be on in order for things to work. So that doesn't work. And then the other thing is that, if you turn the TV on, then the lights would go dim because there's more resistance. So in this case, the voltage is going to be the same. And then as you add on more things, as you turn on a light, you turn on a TV, you turn on a radio, the refrigerator never turns on, or never turns off rather. So all these things are drawing current at the same voltage, but they don't draw the same amount of current. So now we're solving for I. I is V divided by R. So 12 divided by 12 is going to be 1.0. And then 12 divided by 8 is the same as 3 over 2, so that's 1.5. And now we can multiply these together. So this is going to be 12 watts, and 12 times 1.5 is going to be 18 watts. And then, well, our checks, of course, so power 30 is 18 plus 12, that checks out. And then the total current, 1.5 and 1 is equal to 2.5. So that also checks. That's great. But let's just pause here for a second and figure out these two resistors were the same, but we put them in series and in parallel. So who's the big producer? In series, the 12 is producing the most power. Because it has the most resistance, it sucks up more energy as charges try and migrate. And of course, we always have to keep this in the back of our minds, is that it's not like when you turn the power on that these circuits that these wires fill up with charge. They already have charge in them. So as soon as you connect the circuit, positive side starts pushing and the negative side starts sucking in. So everything starts moving at the same time. Over here, the one that draws the most current is the 8. So this is the big user. So in parallel, lower resistance draws more current. In series, larger resistance uses up more voltage. In parallel, so it turns out that a series circuit sounds a lot like stereo. Gonna have to turn that girl down. All right, ridiculous. Well, hopefully things are going okay for you. Let's try something that's a little more complicated. Now, as we start to wade into this, we're just gonna take a look at just trying to get to the equivalent resistance. We can leave that up there. So for what I'm about to do, we're going to say that the resistance for all R's equal 3 ohms. Okay, now I'm not going to do any specific voltages. We're just going to draw it out. So I'm going to have a circuit that looks like this, and I'm going to have 3 in a row. And what is REQ for this? That's something that you ought to be able to do. Same thing, all the R's are 3 ohms. We're going to do parallel. And we want to find out what REQ is. Okay, this would be great. You ought to be able to handle this. So please go ahead and just type in your results into the chat. And we don't need everybody to do that, but just to do a few would be great. All the resistances are 3 ohms. So what's the equivalent resistance for the series circuit? What's the equivalent resistance for the parallel circuit? It'd be helpful if I had the chat on, wouldn't it? Oh, okay, good catch. Yep. That's right. Yeah. Right. So the resistance in series should go up and the resistance in parallel should go down. Yes, very good. Good job. Right. 3 plus 3 plus 3. 9 ohms. And then this is, well, we have 1 over REQ, 1 over 3 plus 1 over 3 plus 1 over 3. Yeah, so that's just equal to 1. And now for shortcuts, we can recognize the fact that if you have 3 of the same things in series, you just multiply by 3. And if you have 3 of the same thing in parallel, you just divide by 3. That's a shortcut. That's legit. Now, here, let's get a little more into it. With 3 different values, there are a total of 4 different combinations that I could draw. Oh, did anybody see that fly here? Mike Pence, we found your fly. Sorry. So
there was a fly on his whiteboard, and he was like, "Whoa, did anyone see this fly here? Mike Pence."
Right, that's not political.
Sorry,
that's
that
just
was
funny.
really funny.
Okay, now I can't draw a straight line. Okay, yeah, so that's one of the combinations you could have, series and then 2 in parallel. All right. Now let's, I'll do another combo. So here's the other way that you could set up 3. Oh, my resistors are terrible. Okay, so we want to find out what is the REQ. For both of those. Okay, well, let's talk about some strategies here. So we're going to have to do this in steps. We don't have any strategies for doing all 3 at the same time. But we do have strategies for dealing with parallel, and we have strategies for dealing with series. So I could replace these 2 with a single resistance, and then whatever I get for a value of having 2 3s in parallel, now that's in series with this 3. And by the same token, I have 2 3s in series. I can combine those. And then whatever I get here is in parallel with the other 3. So for the sake of argument, let's call this circuit A and circuit B. Let's see what we get in the chat for values. So in your responses, you can label them A and B. What did you get for equivalent resistance for A? And then how about for B? That is correct. Okay, let's take a look at the steps here. So through the miracle of the whiteboard, we can just say, okay, I have 2 3s in parallel. So I'm going to have 1/3 plus 1/3, that's 2/3, and then do the inverse of that, that's 3/2, also known as 1.5. So I could just replace this with a single resistance of 1.5. And this is 3, so 1.5 plus 3 is going to be 4.5 ohms. And then I could replace this with just a single resistor, and 2 3s in series is going to give me 6. And then 1/6 plus 1/3 is the same as 1/6 plus 2/6. That's 3/6. And then 6/3 is 2 ohms. That's one of the special combinations that winds up giving you nice, neat numbers for answers. Okay. So that's with a combination of 3. All right. So let's suppose in a quiz situation, I gave you 3 resistors in series and 3 in parallel. Let's see the reactor in the reaction zone. Is that a thumbs up or is that like a thumbs down? And you can abstain if it's more like this. Okay, so I had a few thumbs up. Yeah, that's great. Okay, good. So now let's take a look at one that's on the agenda. So we're just gonna try and put another layer on this. Actually, before we do that, let's do another one. But this time we'll do the chart and we'll see how that works. Okay. So now we'll put some numbers on it. So I'm going to go with 20 volts here. Like this. Okay, now we're going to label them R1, R2, and R3. And so now we'll do our chart again. So we'll do our device, we'll label them, and then V, I, R, P. We'll have our source, and then R1, and R2, and R3. And now let's provide some values. So for the source, that's 20 volts. And then let's come up with some values for R. So let's suppose R1 is 8 and 4 and 6 ohms. And then we want to figure out what the equivalent resistance is. So we should probably do this in steps. And the best way to do this is, well, we know that this is a series combination, right? So let's do a redraw. And we'll put in our 20 volts here. And so if I could find out the equivalent resistance for these two and then replace it just with a single value, and then I can have R3 down here, and we can write in some numbers. So R3 is it's an OR, it's an original resistor, and so that's 6 ohms. Right, and then we have 8 and 4 in series. So 8 and 4 in series is going to be 12 ohms. And I still have 20 volts. And now I have 12 and 6 in parallel, so I can do one more where I cook those down into just a single one and find out what its value is. And so 1 over REQ is equal to 1 over 12 plus 1 over 6. Great. Well, we'll just keep on working it there. You can do this with your calculator. You can do 12 to the minus 1 plus 6 to the minus 1, and then do the inverse of the answer that you get. That's our 21st century way of doing it. Or our 20th century way of doing it is 1 over 12 plus 2 over 12 is 3 over 12, and 12 over 3 is 4. So the load that's seen by the source is going to be 4 ohms. And now I know what the current is. The current's going to be 5. And then 20 times 5 means the power is going to be 100 watts. So I'm going to have 5 amps running through this. But the current is not going to split up evenly because the resistances aren't the same. But I do know in parallel, this is still going to be 20 volts. And this is going to be 20 volts. So since I know those two numbers, I can figure out what the current is for each one. So V is 20, R is 12. And I think you can see what we're doing now is we're actually working backward. We did 2 steps to reduce this, and now we're going to start working backward. 20, this is the place where sometimes people get a little bit lost. So 20 divided by 12, that's telling me that this is, I'm just going to round it off to 1.7 amps. And then 20 divided by 6, the 6 ohm is going to draw more current. How much more? Twice as much. So 3.3 amps. All right, so this was our original resistor, and we can go ahead and write its value in here. So the current for the 6 ohm resistor right here is 3.3 amps. And 3.3 times 6 is 20 volts, but we knew that anyway because it's in parallel with the source. And 20 times 3.3 repeating is 67. So much of the power is shed through that load. Now, when we went this way, this was a parallel reduction. Right, so going this way, this was parallel. And we know the thing that stays the same in parallel is voltage. So when we go this way, we use the same V. This was 20, so this is 20, and that's 20. But when we went here, we did a series reduction. So in going backward, we know the thing that's going to be the same. What's going to be the same about this equivalent resistance and these two is that the current's going to be the same. Right. Okay, so this is going to be 1.7 amps. And this is going to be 1.7 amps. But the voltages are going to be different because the resistances are different. So I can go ahead and write in 1.7 here and 1.7. And now that I know that's the case, then I can multiply them out. So by 1.7, we really meant 5/3, right? All right, so times 8. That's going to give me 13.3. And that's 6.7. I can multiply these out. And I get about 11.1. And I get about 22.2. Okay. Yeah, so that's our first attempt at doing a process that I call circuit reduction. And so I'd like to just try one more example really quick, but let's follow up and let's do our checks. So R1 and R2 are in series. So that's how come they have the same current. So that checks out. And then from here to here, the voltage drop is 20, right? So 13.3 plus 6.7 is 20. That also checks out. Then down here, well, we know the total current is 5. So 1.7 plus 3.3 is 5. We don't want to add these two together because that would be counting the same current twice. So that checks out. And then lastly, if we look at the power, 67 plus 11 plus 22, these two are 33 plus 67 is 100. So that worked. It's going to get a little bit messier. But let's just take one more small step forward and then we'll call it done. I'm going to switch cameras. All right. And then I'll share my screen to take a look at the agenda for tonight. And if you wanted to jot this down, sketch out the circuit really quick. We want to see if we can find the equivalent resistance. And that is right here. So number 20, look, it's level 3 problem. Exciting. And it says each component has R equal to 12. All right, so I'm gonna draw this on the whiteboard. And I'll give you a chance that if you want to like jot this down on a piece of paper or something like that, then you can follow along because this is kind of elaborate, right? Holy cow, what's in parallel, what's in series? Interesting. So I'm going to draw it on the whiteboard and that'll give you a chance to just kind of copy it down. And while you're copying it down, maybe you can think about some strategies. What's in series and what's in parallel? Because this is a nasty combo. There's no voltage given because we're not really We're just looking for the equivalent resistance if they're all 12. Now, just for the sake of conversation, I'm going to label these. So I'm going to call this A and B and C and D and E. Just so we can have a conversation then about, sorry, I forgot to change camera views. So I'll stop sharing. So you can see which ones I labeled as A, B, C, D, and E. Right, hi. There. So A and B and C, D and E. And then we want to try and do circuit reduction. So first, let's try and spot obvious combinations. Because D and E are in series. Are A and C in parallel with each other? No, absolutely not. Why not? Well, because there's B right here. So the current splits up, but they're only in parallel if they split up and then come right back together again without anything else happening. But here's a split, and then I have B and C. Oh, but wait, aren't those in a single pathway? So they're also in series. And if I can reduce that, then that will be in parallel with A. Okay, so let's do a redraw. That's what this is all about. So I'm going to do 2 reductions for these ones that are in series, and then we'll see what it looks like. I think it's going to look like this. So I'm going to come down, and A has not changed yet. So that's A. But then B and C will combine, and I could draw it like this, or I could draw it like this. But I think visually, it probably will be nicer to do it like this. So I'm going to combine these 2 together. And then D and E are going to get combined together because those 2 are in series. So A is the only original one left. It says everything is 12, right? So 2 12s in series is going to be 24. So this is 24 ohms, and this is 24. So it looks like we need to do one more reduction. And that reduction is going to be for these 2 in parallel. But then I think we're going to have it. So this is still 24, but I wanted to reduce these 2 in parallel. And once I get that, then I can just add the 2 together, and then I'll have it. I'll have the final answer. So this REQ is going to be 1 over 12 plus 1 over 24. And I can do that on my calculator, of course. So I can do 12 to the minus 1 plus 24 to the minus 1. And then take the answer and invert that. But I also know that this is 2 over 24 plus 1 over 24. That's 3 over 24. That's 8. So this is 8 ohms. So the final answer is 32. So I'm assuming right now that if you have 3 resistors in whatever combo and you were given a voltage, that you could find out the equivalent resistance and then work your way backward to find V, I, R, and P for each one. But if it's like this is a combo with 5 resistors, I would expect that you can find out the equivalent resistance. But now you can imagine that, you know, if we're going to work our way backward from this to try and find out voltage, current, power, and resistance for each one, that's going to be a bit of a challenge. So we're going to hold off on that. That's what we'll do when I see you on Tuesday next week. Is we're going to work on some of those, and then we're going to revisit. Sorry, we're going to revisit. Yeah, that breadboard. You're going to get it this time, so we'll be there, and I'll do a few things to kind of expedite that as well. All right. So I think that's a good place to stop. Do we have any questions out there? Okay. All right, I'm going to stop recording. And again, if you have any questions that you want to ask me, you could just hang on. And as other people log off.